All right, let's jump right into this explainer. Today, we are cracking open a technology that is widely considered the ultimate Swiss Army knife of system design, Redis. I mean, if you've ever peeked under the hood of a massive, high-traffic architecture, chances are you've found Redis sitting right there in the middle of it all. We're going to break down exactly why it's so incredibly versatile, how it manages to hit those blazingly fast speeds, and how it scales up to handle literal mountains of data. Here's our roadmap for today. 1. The core Redis engine. 2. Fundamental data structures. 3. Practical Redis capabilities. 4. Scaling the infrastructure. And finally, 5. Persistence and data safety.
Let's kick things off with Section 1, the core Redis engine, speed above all else.
So the name itself is actually a dead giveaway. Redis stands for Remote Dictionary Service. It's an open source data structure store written in C. But honestly, the absolute most important words to remember here are in-memory and single-threaded. Because it operates entirely in your server's RAM on a single thread, it completely bypasses all those complex query planners you'd find in traditional databases. It just executes simple operations, and it does it incredibly fast. And this brings us to a massive, fundamental trade-off that the creators of Redis made. By prioritizing in-memory speed, Redis can easily handle around 100,000 writes per second with read latencies down in the microseconds. It's wild. But the trade-off, well, you sacrifice out-of-the-box disk-based durability. Traditional relational databases lean heavily on slow disk writes just to guarantee your data is totally safe. Redis chooses speed every single time.
Moving right along to Section 2, fundamental data structures more than just strings.
You know, instead of iterating over rows in a rigid SQL table, Redis actually lets you play with native data structures directly. Sure, you have your basic strings and hashes, but you also get some seriously powerful tools. Things like sorted sets for easily managing ordered data, and Bloom filters for probabilistic checks. A Bloom filter is basically a super efficient way of asking, hey, have I seen this item before? Without having to memorize the entire list. You even get geospatial indexes and append-only streams. And the best part? It's all manipulated via a highly readable custom query language. Okay, Section 3. Practical Redis capabilities, beyond simple caching. Now, the most common use case for Redis, hands down, is caching. You might store a product's details as a native hash, but obviously memory is finite. Enter the TTL, or time to live. By slapping a TTL on your keys, Redis absolutely guarantees you will never accidentally read stale data once that timer ticks down to 0. It automatically evicts the expired items. It's essentially taken out its own trash, which keeps your cache size perfectly manageable. Let's look at another huge use case, and think of this one kind of like a race, the distributed lock. Imagine you have multiple clients trying to access the exact same shared resource at the exact same time. Here's how you solve it. A client runs an atomic increment command with a TTL. If the response comes back as a 1, boom, congratulations, that client won the race and now owns the lock. If the response is greater than 1, someone else already beat them to it, so they just wait. When the winner finishes up, they simply delete the key, releasing the lock for everyone else. It's just a beautifully elegant way to maintain system consistency. But man, the versatility really doesn't stop there. Need a high-speed live leaderboard? Just use sorted sets to query rankings and log time. Building an API and needs some rate limiting? A simple increment and expire command will instantly build you a fixed window counter. Making an Uber-style app? Geospatial indexes will find items in a specific radius almost instantly. Using these native capabilities prevents you from agonizingly overloading your traditional SQL database with operations it just frankly wasn't built to handle. All right, on to Section 4, scaling the infrastructure from single node to cluster. Most people generally start with a single instance. It's super simple, but it is a massive single point of failure. If that node dies, your cache dies right along with it. So the first logical step up is adding a high availability, or HA, replica. The main instance asynchronously syncs its data over to a secondary one using a replication ID and an offset counter. If that secondary node ever falls behind, it literally just asks the main instance for the missing commands based on that offset. Once the ID and offset match, boom, they are perfectly in sync. But wait, what happens if that main instance physically dies? You need a way to automatically promote that secondary replica. Enter Redis Sentinel. Sentinel is basically a distributed system of watchdogs. They actively monitor your instances, manage the configurations, and execute automatic failovers. But to prevent Sentinel itself from becoming a single point of failure, these watchdogs actually have to agree with each other. They must reach what's called a quorum consensus before they can take any drastic action. If we look at the math behind that quorum, notice a specific pattern in the total servers column? Yep, they're all odd numbers. If you have 3 Sentinel nodes, your quorum is 2, which allows for exactly 1 failure. Running an odd number is an absolutely crucial best practice because it effectively acts as a built-in tiebreaker during a split-brain network failure. It guarantees your watchdogs can always reach a solid majority decision. Now, what if one massive main instance still just isn't enough memory for you? You have to scale horizontally. Redis cluster achieves this using algorithmic sharding. You take a key, hash it, and use modulo arithmetic against your total number of shards to decide exactly which node it lives on. But there's a huge catch here. If you add a new server, your total number of shards changes. That completely breaks your modulo map, forcing you to move massive amounts of data around just to rebalance the entire cluster. To solve this absolute math headache, Redis introduces a brilliant layer of misdirection: hash slots. There are exactly 16,384 hash slots in a Redis cluster. Think of them kind of like a gigantic distributed phone book. Your keys map to the hash slots, and the hash slots map to your physical servers. This way, when you add a new server, you don't have to recalculate every single key. You just move chunks or batches of these hash slots over to the new hardware. It is incredibly efficient. However, even with perfectly distributed hash slots, you can still run into the dreaded hotkey problem. Imagine you run an e-commerce store and one specific item goes absolutely viral. The single server holding the hash slot for that one item is going to get completely hammered with traffic, while the rest of your expensive cluster just sits there idle. To fix this, you have to design specific remediations, things like in-memory client-side caching or dynamically adding read replicas just to absorb that massive surge. And finally, Section 5, Persistence and Data Safety, Safeguarding Memory. Redis offers 2 main persistent solutions, and they both have their own trade-offs. First up is RDB, which takes point-in-time snapshots of your entire dataset. These are incredibly compact files, and they load blazingly fast. But if the power dies between those snapshots, you lose all that intermediate data. The second option is AOF, or append-only file. This essentially logs every single write operation as it happens. It's way safer, but the files get much larger and they're slower to load. The best part, though, you can actually configure Redis to use both, giving you the speed of RDB combined with the safety net of AOF. But this brings up a rather massive technical hurdle. We established very early on that Redis is single-threaded. So how on earth does it suddenly copy gigabytes upon gigabytes of data to a slow disk snapshot without completely halting the entire system and blocking all your active users? Well, Redis pulls off a really slick operating system level trick called forking. When it's time to take a snapshot, the main Redis process literally forks itself, creating a hidden background child process. And thanks to the OS, this child instantly shares all the existing memory references with its parent. The child process goes off to handle that slow disk write completely in the background, while the main thread just happily keeps serving your active clients without so much as a hiccup. And this builds directly into the pure genius of the copy-on-write mechanism. Now, you might be thinking, doesn't spawning a child process duplicate all that data and instantly double your memory usage? Nope. Because those memory pages are shared, the kernel only allocates new memory if a specific piece of data actually changes while the backup is running. If the data isn't touched, absolutely no new memory is used. It's just a wildly efficient way to snapshot gigabytes of RAM. As we wrap up this explainer, I want to leave you with a final thought. We've seen exactly how Redis operates, from its single-threaded core right up to its clever scaling and persistence tricks. Knowing these architectural trade-offs, take a really hard look at your current projects. Where could you replace a slow, complex database query with a lightning-fast Redis structure? It's definitely something to think about. Thanks for joining me on this deep dive, and I'll see you next time.